other types of professional involvement. Tonight we feature a poster presentation followed by an oral presentation. The poster will be presented by Xiomara Martinez, who is a PhD candidate at Loyola University Chicago, Department of Chemistry and Biochemistry. The technical talk will be given by Fred Foster, who is an application scientist with Gerstel. Let me start with a few housekeeping matters. First, as the poster appears on your screen, you may want to change the layout in the upper right corner of the screen to side-by-side format for the best perspective. Second, Zio will present her work for 10 minutes. This is the poster, followed by 5 minutes for questions. If you have a question at any time during the talk, please post it to chat and we will field questions at the end of the presentation. Any questions that we cannot get to tonight can be directed to Zio at her Loyola email address, which appears on the poster. Last, we will follow the same question and answer protocol for the oral presentation by Mr. Fred Foster. And now it's my great pleasure to present Ms. Xiomara Martinez from Loyola University, Chicago.
Thank you, Dr. D, for that introduction. Like he said, I am a PhD candidate at Loyola University Chicago in the Department of Chemistry, and I will briefly be discussing my research on the photolysis of emerging contaminants absorbed onto plastic in an aqueous environment. So the overall goal of this research is to see how synthetic plastic influences the phototransformation of certain contaminants in a laboratory setting, so using artificial light. Now, as you all are aware, plastic debris does cause harm to our environment and to the health of a variety of species, including humans. Particularly in aquatic environments, microplastics can become a sink for persistent organic pollutants such as polychlorinated biphenyls and polybrominated diphenyl ethers. These toxic chemicals can then be transferred to aquatic species and then can be transferred to humans in which they bioaccumulate. Previous studies we've used the polymer polyethylene, and it was shown that phototransformation on polyethylene is a lot faster than when not used. After that, we expanded to other plastics that contained aromatic structures in the group, such as polystyrene, shown here, and also polycarbonate. So today, not only am I going to be discussing how the type of plastic may influence the phototransformation, but also the surface area. And the three plastics, again, that I will be discussing are the aliphatic polymer polyethylene and polymethyl methacrylate, which is sometimes used as a cheap substitute for glass. The reason why we chose polymethyl methacrylate was because just like polyethylene, it doesn't contain any aromatic groups in its structure. Therefore, we are hypothesizing that we should be seeing similar results to polyethylene. And then the reason why we chose polystyrene, shown here, is because it does contain that chromophoric group in its structure. Thus, it has more light absorbing capabilities near 300 nanometer wavelengths. Unlike polyethylene and polymethyl methacrylate, which have really low light absorbing capabilities at that wavelength, if any. Our compound of interest, our model compound that we started with, is triclosan, shown here on the left. Triclosan is a common antimicrobial agent found in a variety of consumer products. It has been detected in a wide variety of matrices. And recently in 2016, it was banned from over-the-counter soaps. And also most recently, it has been removed from Colgate's toothpaste. It has been shown to be toxic to aquatic species, and there's also research that it causes reproductive issues in humans. Triclosan is photoactive, and under certain irradiation conditions forms 2,8-dichlorodibenzoldioxin and HCl. I will be referring to this compound as 2,8-DCDD. 2,8-DCDD has also been found in the environment, such as in sediment and in surface waters. It has been detected in toothpaste and in mouthwashes that contain triclosan. It has been shown to be lethal to goldfish. And unlike its most toxic cousin of 2,3,7,8-tetrachlorodibenzodioxin, 2,8-DCDD has a lethal dose in guinea pigs of 300,000 micrograms per kilogram compared to 2,3,7,8-TCDD, which has a lethal dose of 2 micrograms per kilogram. Regardless, it is still something important to evaluate and to look at. Now, I will draw your attention to this graph down here so we can discuss the experimental portion of the first half. So for the first half, what we did is we took 5 irradiation times from 3 to 20 minutes, and we irradiated at 300 nanometers for each time point. So each time point contained 3 different aqueous solutions of triclosan containing 3 different types of basically surface areas of polyethylene. So what we did is we ordered polyethylene from the company Cospheric, and these polymers had well-defined diameters. So to have a more controlled environment in our experiment, we ordered all the plastics from one single company. In this case, for each time point, the concentration of triclosan was the same, the irradiation time was the same for each sample, and so was the wavelength. The mass of the plastic was also the same. The only thing that changed was the surface area. So the dark blue being the sample with the highest surface area, and then the lightest blue being the sample with the smallest surface area. After we irradiated our samples, we extracted any photolysis products via liquid-liquid extraction, and any products formed on the actual plastic surface itself was extracted via sonication. We also irradiated samples without plastic as controls. So for our analyses, we actually analyzed all our samples via GC mass spec. We use a Agilent 6890 in the positive EI mode. A linear GC gradient was used from 32 to 300 degrees. And then we use a total runtime of 20.9 minutes. And 1 microliter of sample was injected for analysis. So if I can draw your attention back down to the graph again. At the bottom, we have our irradiation time on the x-axis. And then on the y-axis here, we have our abundance ratio of our photolysis product, 2,8-DCDD, over triclosan. And as we can see, from 3 to 10 minutes, the rate of decomposition increases. But what we also see is that as the surface area of the polyethylene increases, so does the rate of degradation. And we can attribute that to having, for the triclosan, having obviously more surface area. After 10 minutes, we don't see that anymore. And what we're hypothesizing is that 2,8-DCDD, our decomposition product, is decomposing at that point in irradiation. For our next experiment, shown here on the right, see if I can zoom in a little more. We looked at two different types of plastic along with polyethylene. Again, we looked at polystyrene because it contained that light-absorbing chromophoric group in its structure. We looked at polyethylene because that was the original polymer that we did our initial studies with. And then we used polymethyl methacrylate because we were hypothesizing that it would behave similarly to polyethylene. Once again, all of these polymers were purchased from Cospheric, and they all had defined diameters. In this case, we couldn't have polymethyl methacrylate or polystyrene have equal surface areas. So what I did is I use a surface area of polyethylene greater and also smaller than their surface areas. Once again, we did the same thing as before. We made aqueous solutions of triclosan, so each sample had the same amount of triclosan, the same amount of plastic, same irradiation time and wavelength. The only difference was their surface area. And what was interesting to see is that the polymethyl methacrylate kind of behaved similarly to polyethylene in terms that from 3 to 10 minutes, the rate of decomposition of triclosan did increase. But if we draw our attention to 10 minutes, we see that the surface area of polymethyl methacrylate is smaller than the surface area of polyethylene. But the abundance ratios are relatively the same. Because of this, we are hypothesizing there is some sort of different interaction between the triclosan and the polymethyl methacrylate surface area. Now, when it comes to polystyrene, the abundance ratios aren't as high as with the polyethylene and polymethyl methacrylate. And this is something we have seen in the past with our previous studies done with polycarbonate and polystyrene as well. And what we're hypothesizing is that because these synthetic polymers that contain these aromatic light-absorbing groups in their structure, triclosan is transferring energy to these polymers, versus when triclosan is irradiated on polyethylene or polymethyl methacrylate, these aliphatic structures aren't, triclosan isn't transferring energy to these polymers that do not absorb light readily near 300 nanometers, like polystyrene and polycarbonate, for instance. Down here is some of the results from our controls where we irradiated samples without plastic. As we can see, we're seeing the same thing. The polystyrene is inhibiting that triclosan decomposition. And then triclosan without plastic, the decomposition isn't as substantial as when it is irradiated with the plastic. So just to conclude, We investigated how different types of plastic influence the decomposition of our model compound Triclosan, and our study suggests that as the surface area of the plastic particles is increased, the rate of the decomposition increases. We also see that polystyrene has a low abundance ratio compared to polyethylene because, again, polystyrene is aromatic and is better able to absorb near 300 nanometers. The results obtained with polymethyl methacrylate suggest that the interaction of triclosan with the particle surface is different. And after 10 minutes, what we are seeing is that the initial product of the radiation begins to degrade further. In the future, what I have done is I have calculated the actual mass I need for these plastics for them to have the same surface area. And we have also, because unfortunately we can't order polycarbonate co-spheric beads, so what we've done is we transformed those beads in the lab itself. I would just like to end by thanking the Chicago Chromatography Discussion Group, and I am open to questions now.
Okay, great. Thank you very much, Zio. If anybody has any questions, they can place them in the chat. We have about 5 minutes allocated for questions. Zio, I'm going to go ahead and start this off with a question. Triclosan will also decompose into the dichlorophenols.
Yeah,
did you guys monitor the dichlorophenols at all?
We did not monitor any other products.
Okay, all right. The other question was about the difference that you saw in the decomposition based on the different polymers. Did you consider doing like a quenching experiment with sort of a stand-in for the polystyrene, something like ethylbenzene, just to see if you increase concentration of the ethylbenzene, if that acted as a quencher?
We have not. I think we kind of wanted to steer away from benzene compounds, but
right.
But we have thought about it.
Okay, all right. So I do see a question came in. Is it possible that the 2,8-DCDD is further reacting to other photolysis products?
Yes, that is a great question, and that is something that we are actually looking at the moment.
Okay.
Yeah, it is possible.
All right. Any other questions at this point? Okay, so I'm going to go ahead. I'm going to go ahead and turn things over to Joseph and take it away.
Excellent. Thank you, Zio, for sharing your research with us tonight. Excellent job on that.
Thank you.
So next, our presentation tonight, entitled Automation, the next critical tool for scientist survival during the pandemic and during recovery. This is a very timely and relevant presentation for everyone in the laboratory field. As we've navigated the pandemic landscape of the past year and prepare to navigate this post-pandemic recovery, automation will play a very important role in the laboratories who end up thriving and those that end up not thriving. So our speaker tonight is Fred Foster, who is an applications scientist with Gerstle, based out of Baltimore, Maryland. Fred holds a BS in chemistry from Juniata College and a Master's of Science in Biotechnology from Johns Hopkins University. Mr. Foster has more than 25 years' experience in analytical and bioanalytical method development and analysis. Fred spends a lot of his time developing, demonstrating, and training customers on automated sample preparation methods coupled to either HPLC or LC-MS. So please join me in giving Fred Foster a warm CCDG welcome. Fred, take it away.
Thank you, Dr. Jones. I appreciate that. as I was, let me see if I can have, there we go. Full disclosure, as I was creating this presentation, I kept coming back to the title. And although it's catchy, it could be construed as maybe a little over dramatic. And so I just wanted to make sure that everyone is aware that these are actually the three most important tools for us during this pandemic. 6 feet, mask up, wash your hands, happy birthday twice. And as soon as you're able, get the vaccine. Those are going to be the most critical. But that being said, this pandemic forced everybody to learn how to continue to be productive while existing in a remote environment. Now, as scientists, we were able to quickly adapt to virtual meetings, web conferences, and online connections, as this one. However, our workloads, right, and the samples that still need analysis, did not stop. There's still laboratory work to perform, and that work is harder to complete remotely. So once everyone has been vaccinated and the ever-present curve has finally been flattened, that brick and mortar work environment will open again. And once that occurs, all that work that was delayed as a result of shutdowns or partial work weeks or working from home will still be waiting for us. So we're going to need a way to do a lot more with less resources, unless we're able to grow a couple more arms. That is why automating as much as possible will be critical. So for those of you who may not be aware, Gerstle, the company I work for, provides sample preparation and introduction systems for chemical analysis with an emphasis on innovative automation. So the MPS, or multi-purpose sampler, is a highly efficient LC or GC auto sampler with extended robotic functionality. So it provides reliable processing of complex tasks, including like liquid extractions or solid phase extraction procedures, as well as other liquid handling methods. The syringes used in these systems are integrated in special modules, which can be exchanged automatically during a running sequence when using the MPS for maximum flexibility. And the entire system is controlled using Gerstle's Maestro software, so it conducts all those automated procedures that you may want to do. So, of course, shown here on the left is the MPS is configured with a GCMS. On the left, or the other left, on the right, it's configured with an LC or LCMS, but it also can be used as a standalone workstation. So you could automate your sample preparation methods on a workstation that then you can take the samples to whatever analytical technique that you need to use for that day. So why do we automate? All right, so whenever we're automating, we're looking for consistent accuracy and precision for the analytical method. The robot's going to do something the same every single time. It also allows you to control the experimental variables. So if we need to derivatize, every sample is going to be heated at the same temperature for the exact same time, and you're able to control all those variables without, like if you're doing it manually, you might forget for one step or what have you. We're also going to lower costs through miniaturization, right? So we're going to use less solvent. We're going to use less sample. Those deuterated internal standards can get really expensive, so it's important to control those and lower the costs. And that lower amount of solvent, it's also going to make it safe for people to work because you're not exposed to potentially hazardous material. The other nice thing, and this will be important for us, especially going forward, is that increased productivity, because robots can work 24 hours a day, 7 days a week. They don't, have sick time or vacation time or need to sleep. And that allows us as analysts to make better use of our time, making the important decisions that we have to make based on that data, and interpreting the results. So these are the two most important for us moving forward whenever we're getting back to work with all those samples that need to be analyzed. I saw this on the internet the other day, and I can't tell you how many times I probably too aggressively thrown out vials or test tubes whenever I'm making calibration curves because I'm pipetting everything and I've focused, and a minute will go by and I'm like, I don't know if I added internal standard to that sample, and I can't remember, and it's too important not to know. So you got to start over. The robots don't forget. They're always focused. They don't get distracted. That's another big benefit of automating as much of the preparation as you can. So let's think about some of the most time-consuming steps that we as scientists and chemists are performing each day that could be automated. If we're quantitating our samples, we may need to add an internal standard in order to quantitate, or if we're analyzing by GC, we may need to derivatize a standard by adding derivatization reagents. That's a liquid handling step that can be easily be automated. Some of us may need to filter our samples. A lot of the UHPLC columns are using the very small particles, and you really got to be careful that you don't have particulates in your sample. Or if you're doing GC, you want to make sure that liner is cleaned. You may need to filter your samples prior to analysis. If we are quantitating, we may need to prepare calibration curves, sometimes every day. Or even if you're just doing a single point, or standard addition, you may need to add a surrogate or a standard to your sample. That can easily be automated. Depending on how regulated you are in your work, you may need verification of exactly how much solvent or how much internal standard you've added each time you are creating your samples. And a verification for documentation purposes, at the least, would be a nice manual step that would be nice to automate. A lot of times we'll need to solubilize samples. We'll need to dilute them if they're too high for our curve. We may need to heat them or mix them to get them into a form that we can then present to our LC or LCMS. If you are extracting, for example, if you're doing like liquid extractions or even the catchers extractions, if you're looking at pesticides, once you do a gross extraction, you'll want to sediment, down some of the particulates, or you need to form the bilayer in a liquid extraction. And so centrifugation is one manual step that would be nice to automate as well. Not only for liquid extractions, but if we are doing those, once we've driven our analytes or partitioned them into that organic extraction layer, we may want to evaporate it in order to concentrate the sample and improve our detection limits, or even to exchange the solvent into more LC amenable solvent per injection, or GC even in that case. And we may even need to do a little more thorough cleaning of samples prior to injection. For example, solid phase extraction, which would be really nice to be able to automate prior to injection. Another full disclosure, I should say, at Gerstle, I do a lot of LCMS work. More LCMS than the other thermal desorption and GC work. So a lot of my slides show LC, so I usually default to LC. But in any event, Gerstle has sample preparation options that will allow the user to automate each one of those extraction steps. We can automate a variety of different mixing. We can cool samples if they're temperature sensitive. We have a variety of different SBE options, and they're all modular in design. So you can configure your system to be able to perform your exact procedure as either a workstation or, as shown in the picture here, online with your LC or LCMS system or GCMS system. So as an example, let's pretend that we have a liquid extraction procedure. We're going to quantitate, so we need to add an internal standard. But because we work in a regulated environment, let's say, we need documentation and verification that we added the exact amount of the known internal standard. Then during a liquid extraction, of course, you may want to adjust the pH of your sample, either by adding acid or alkaline buffers in order to control that pH and help drive our analytes into the extraction solvent. Then we'll add the extraction solvent, of course, and then by mixing, we'll help partition that analyte into the extraction solvent, centrifuge to form the bilayer in order to be able to transfer that our analytes that are now in that liquid layer into a separate vial. Once we do that, we may again evaporate to dryness and then reconstitute to concentrate and achieve our limits of detection. So if we take this basic liquid extraction, depending on your workflow, a lot of labs need a little more verification. If you are in need of barcode reading capabilities to track, to make sure that you're using the correct standard or correct internal standard by a barcode, we have Barcode Readers. SID stands for Sample Identification. And here, we can read either a 1D or a 2D barcode, and the Maestro software lets the user choose whether they want to check to make sure that that's the correct barcode, or just read the barcode and put that data into a file automatically that's stored with the data once it's analyzed, or in a CSV file for documentation purposes. So that's a possibility. And then once we know that we have the right internal standard, we'll add that, but we need the verification of exactly how much we add. So shown here is the Sartorius Balance option. Now we can use both Sartorius or Mettler-Toledo balances. That's up to the user, but what we would do is the vial with the sample would be magnetically transported to the balance, and the weight would be recorded, and whatever weight is displayed on that balance is automatically transferred to the computer and stored as a CSV file. Then the MPS would pick up the internal standard and add that to the vial, and then the vial would be transferred back to the balance and reweighed. And the user could then go into that CSV file and open it up to determine exactly how much of the internal standard was added to that sample. And then, for each sample, the same thing would be done, and you would have a running list of exactly how much internal standard was added to each of your samples. Once we have the internal standard in there, we'd want to add our buffer, right? Now, of course, the syringes are easily able to add, known amounts of buffer or solvent. But for adding larger volumes, we have what's known as a diluter module. And as shown here, there's actually a 5-position diluter module. So this lets the user select in the software by a drop-down menu. For example, let's add the buffer. So they select in the software and let them know how much, what volume to add to the sample. And the MPS would then go over to the vial and add the buffer. And then once it's time to add the extraction solvent, you would select in the drop-down menu, add the solvent, what's the volume, and then it would allow him to do that as well. So it's an easy way to be able to add a larger volume of diluents or buffers or solvents to a sample relatively rapidly. Once we have our extraction solvent and buffer in our sample, we're ready to extract it. And our agitators are all orbitally shake the samples. They're capable of heating and mixing the samples. We also have stirred versions of the agitators. That's usually used with doing SPE analysis. It's more efficient to stir the sample. So, the user will put a magnetic stir bar in a 20 ml vial that has the sample, and then the MPS will move it over. And then whenever it's time to stir it, you just, the command is stir, and it stirs the sample. But we can also have agitators for larger vials. So if your method required a 40 ml VOA type vial, we can still shake those up. Or, if you needed to cool during agitation or derivatization, we have ability to do that as well. But for a liquid-liquid extraction, our mixing unit of choice, I would say, would be what we call the quick mix. So the normal agitators will agitate at maximum speed of 750 RPMs, which is good to mix a sample. But if we want a really vigorous, quick agitation or almost vortex mixing, we would go with the quick mix because it's able to agitate up to 3,000 RPM. So, and all the user needs to do, is shown here, is choose what size vial they're going to use. And there's trays for each size vial. On the left is a 4 ml vial tray, and on the right there is for 20 mils. But to give you an idea of how vigorous it is, we actually had an application note that looked at determining antibiotics in egg samples. And as shown in the pictures here, what I did was I put some egg and the extraction solvent in a vial, and then mixed it in an agitator up to the maximum speed, that's 750. And you can see I got some mixing after 2.5 minutes, and then I did it for a little longer. And then, as soon as it's done, I take it out and take a picture. But you can see at the bottom there, the quick mix, that's not even the highest speed, but that is a super vigorous mix. I was able to get the maximum mixing and only had to use 2.5 minutes to get that mixing complete. For people who may need to use a sonicator, like future Dr. Martinez, whenever you're analyzing or trying to extract plastics, or for people who are doing soil extractions or other things, they may need to sonicate their samples during the extraction. We have sonicator options. The vials are transported in. The software is able to control the start and stop, as well as, however, the length of time. So you can accurately and precisely control the time of sonication so that that's one control point during your experiments. And then, it'll move the vial back and further process the sample. So once we have our liquid-liquid extraction well mixed, then we'll need to centrifuge it in order to form the bilayer. Shown here is what is known as the Cf200 centrifuge. This option actually has rotors for either 10 mil or 2 mil vials. There's 6 positions for each. And at 2000 G, that's able to really separate those two layers from our sample and extraction solvent. Or it's also able to sediment down particulates that may be in the sample, or if you're doing the dispersive SPE, it will sediment down that sorbent at the end. But irregardless, once we have our samples centrifuged and we have that layer, the MPS using the syringes can transfer user-defined volume that now has our analytes of interest in to a new clean vial, and then we may want to evaporate it to dryness in order to concentrate it. We have a unit called the multi-position evaporation station. So that's a MVAP for short. You notice that we have a lot of acronyms for all of our sample preparation options. But this unit, the red unit shown here, is still a heated agitator, right? So the agitator sample will be placed in the MVAP, and then our gripper mechanism that's integrated with our syringe tools will pick up that vacuum adapter and place it on the vial. And then the user in the software can control that blue vacuum pump. So we're reducing the pressure in the vial, we're heating the vial, and it's agitating, which will allow that solvent to evaporate off in a quick amount of time. And then once we're finished, since it's still an agitator, the gripper can move that vacuum adapter off the vial, and we can go pick up a reconstitution solvent from a location on the MPS and add that to our vial, and then quickly mix it to reconstitute the sample, which then can be injected into our system or further processed if we need to. So to give you an example of what that software looks like, this is the Maestro software. It's all based on prep and loops, so any of the steps are found in the loops will be repeated for however many vials you need. I'm going to zoom in for you to show you that the preps methods they're easy to understand. If we wanted to weigh our vial, we use a wave command. If we need to add an internal standard, we need an add command. So it's very easy to understand and very easy to pick up on how to program the MPS using the Maestro software. Now, the other nice feature in this software is what we call the prep sequence scheduler. And this is showing the user a graphical representation of exactly what's going on during our automated liquid-liquid extraction. So you'll see we're enabling some prep ahead feature that is available in the Maestro software. For example, the yellow bars here represent that the software has said, it's more efficient for me to move a sample in and start mixing than to mix one sample in series, and then second sample and then third sample. I can really maximize the use of my time. In addition, there is a real-time status bar that is located to the left there that will start to move during the course of the run. And so if you go out of the laboratory to, review your data or get a cup of coffee or whatever, and come back in, you'll be able to tell exactly where you are in the prep sequence by that real-time status bar. And then it also, at the bottom there, it will give you an estimation of the total time it's going to take for your prep sequence. So that helps whenever you're developing methods to make sure that you're using the most efficient method and you're increasing the throughput as much as possible. This I was speaking of the antibiotics and eggs application that we had. This is more details on that. We basically started with 2 grams of egg. In this case, I pipetted the internal standard myself, but the MPS could easily do that as well. But as you can see, we can mix and match techniques. So I started by doing the liquid-liquid extraction with the egg sample. But eggs are a lot of what an egg is phospholipids, and I'm analyzing antibiotics by LCMS. So in order to minimize the matrix suppression from phospholipids, we really need to clean those up. And what we did was we passed that extract through a prime HLB cartridge, and that's going to retain those phospholipids and then leave us with a cleaned extract that we can then analyze for the antibiotics that were present. In this case, after we passed it through, we further diluted it in order to get it into a more mobile phase composition for the injection for the chromatography. So the use of that that HLB prime HLB was actually in a set pack format, and what we did was we used our universal filtration option to perform basically a chemical filtration, right? So in the top left there, you can see the gripper mechanism that's integrated with our syringe modules. That'll be used to transport these filters to the various locations on the MPS that it needs to go. And on the bottom left there, you can see the user has the ability to choose whichever size or style syringe filter that they may want. All we do is affix a transport adapter to the top of it so that it can be moved along the MPS. And we put a syringe needle on the bottom so that we can collect the filtrate or the eluent into a sealed vial to make sure we avoid cross-contamination from sample to sample during the filtration. So in the middle here, that's that prime HLB set pack format cartridge that we used. Set pack is also, that style is used on the left there. That's actually a DNPH cartridge for a different type of analysis. But you can see we can also put a filter on the bottom of that cartridge. So we could do, a chemical filtration plus a filtration using a different membrane if we wanted to. But as shown on the right there, we basically passed our extraction extract through the cartridge. It retained those phospholipids, and then we were left with a clean extract at the bottom of our vial that we then analyzed for the antibiotics. Just real quick here. Again, this is I'll zoom in for you. This is the software that was used. This is the program that was used. Easy to understand again. Add, mix, move. We used the elute command to control the filtration through the cartridge, and then ended up with the inject because it was online. In this case, we used our LCM. The triple quad was the Altivo, is what we were using for the data analysis. You can see, we performed, calibration curves and QCs. We got excellent, reproducibility and accuracy on the antibiotics that we were looking at, as well as we realized good calibration curves. The blue dots are the QCs, and the black circles then are the standards that we were using, and we were able to get good chromatography for an extracted sample that there is an extracted low QC, showing that we got some good chromatography on that. But most importantly, through this automated extraction, was we were able to clean up all those phospholipids. So what we did here, what we're showing here is I basically just monitored, the normal phospholipid M over Z, and then I extracted a sample and passed it through the cartridge, right? So I cleaned it up. That's that red trace at the bottom where you don't really see anything. And I extracted a sample but did not pass it through that HLB cartridge, and that's the purple trace showing all those phospholipids that could potentially lead to matrix suppression in your analysis, and could lead to irreproducible results, and ruin your limits of detections. For people who are are afraid of building the prep sequences, we offer wizards. So for this, in this case, for preparing calibration curves, we can automate the preparation of the prep sequence, basically. So we're automating the creation of the method. All the user needs to do is tell the software, hey, Maestro, here's where my diluent is. here's where my internal standard is if I'm using an internal standard. My stock solution is located here, and this is the concentration. And then the user is able to actually put in what concentrations they would like prepared and where to place them afterwards. And the Maestro software will automatically generate the prep sequence for that to create those calibration curves, as well as provide a graphical representation of exactly how to do that. So it automatically knows, I need to mix a sample before it transfers it. It automatically knows in this case that L1C and L3C, those are intermediates that had to be prepared. It knows that those would need to be prepared and automatically populates those within the software. And then the user just needs to press go. After making sure all the vials are on the MPS. As I mentioned, we also can automate a variety of different automated solid phase extraction techniques. You may be familiar with the micro SPE, those miniaturized SPE cartridges. In the center there, that represents the barrel style, the traditional SPE cartridges, 1, 3, and 6 mil, and as well as dispersive SPE. So shown here on the right there is a disposable pipette extraction or DPX tip. So as a good example of the use of the automated micro SPE, Steve Lahote, and the inventor of catchers, and his group at the USDA is using the MPS and Maestro software in order to perform that second step of catchers. So the first step is the gross acetonitrile with the food and the buffer, and you mix that up manually. And then once that's done, you place an aliquot of that acetonitrile extract into a vial, and then the MPS takes over and will pass that sample through the catcher's micro SPE cartridge, automatically add the internal standards or analyte protectants that it needs, and it does so during the course of the analysis. So he uses low pressure GC triple quad for his analysis, and I think it's about a 14-minute run or so. But the Maestro software is able to perform all that sample preparation within the same time frame of the analysis. So a sample's ready as soon as the first sample has been analyzed, and it maximizes the throughput of that catcher's type analyses. We can also automate, like I said, the traditional barrel style SPE cartridges. So shown here on the bottom, there's the traditional barrel. All we do again is affix a transport adapter on the top so we can move it to the various locations that it needs to be. And again, a syringe needle on the bottom so we can elute into sealed vials. And as you can see here, our syringe basically becomes the barrel of the SPE. So we add the conditioning and equilibration solvents, we add the sample and then wash it if we need to. And since the syringes being used with the SPE option are a headspace style syringe, the MPS can actually be plumbed with an inert gas, like nitrogen can be plumbed to the MPS and delivered through the cartridge if we need to dry it prior to elution. And then once it's eluted, we can then either inject it or evaporate it or whatever we need to do next. I mentioned dispersive SPE. We have what we use is the DPX technology. That's dispersive pipette extraction. So that's solid phase extraction in a tip. This uses small volumes, of course, which means lower solvent volumes means lower amount of waste. It's really reproducible because the efficiency of this solid phase extraction technique is based on the equilibration time with the sorbent, rather than dispensing it at a consistent flow rate through a cartridge which is really, easy to control. Time's easy to do. An example of this, we had a recent application in which it was for fentanyl and various opioids in urine, but we actually automated the hydrolysis step as well. In this case, we used the ICM-enzyme to beta-glucuronidase to hydrolyze the urine. So the MPS would add the beta-glucuronidase, the buffer system, move it to the incubation location for controlled temperature and time. And then once that's hydrolyzed, the MPS can transfer a known amount into a vial. And then as shown here, in the case of DPX, you actually aspirate up the sample into the pipette tip. And then by mixing with air, you get that turbulent mixing. The analyte is able to partition to the sorbent that you're using. And then since there's a tapered frit on the bottom of each DPX tip that retains the sorbent but allows the liquids to pass through or the sample to pass through, so you can dispense out the matrix, wash it if you need to, and then lute off the compounds of interest in order to further analyze. Now this is more probably apropos to people doing LC or LCMS work, but we can also automate online SBE using the Spexos unit that we have. That's an online SBE with cartridge exchange. So you're able to introduce a new cartridge for each sample. Since they're smaller cartridges, they have they're a lot smaller particle sizes than normal SBE cartridges. And so you get a more tight band, like an LC, like separation band. There's still all the sorbents are available, but the benefit to online SBE is as compared to like traditional SBE, you elute off your analytes with, let's say, 500 microliters of solvent, and then you inject 2 microliters of that. Well, online SBE, once you've cleaned up your sample and you have your analytes on your cartridge, that mobile phase is sweeping the entire contents of that SBE cartridge onto your LC and then your LCMS system, and you're getting 100% of the analyte transfer. So that really lowers your limits of detection without any need of evaporation. There's an example application that we used is glyphosate is extracted. Typically, you have to derivatize first with FMOC, which we showed in the application that we can, add the derivatization reagent, derivatize the extract, and then pass it through the online SBE for cleanup and then further analysis by LCMS. All right, just some quick examples of, offline workstations, how we can configure these to do, just prepare the samples for analysis offline. I had mentioned before the DNPH cartridges. Those are typically used for scientists that are looking for aldehydes and ketones from air. So what they'll do is they'll pull air samples through the cartridge that is embedded with the derivatization reagent, that DNPH. And then as that air sample is being pooled, any aldehyde or ketone will be held up and derivatized at the same time. And then typically what they have to do is bring those into the lab, elute them off with acetonitrile, filter the sample, and then inject it into the LC. But using our universal filtration option, we can easily automate that. And then using the balance option shown here, we were able to collect data with showing exactly how much eluent that we were collecting, which means that we can then trace that back to have a more accurate amount of whichever aldehyde that we had collected on the cartridge during the air sampling. For some of the oil chemists out there, the edible oil market, one of the latest contaminants that's been of interest is 3-MPCD, and glycerol. We have an application note showing how we can automate this extraction. Again, the modular design of all our sample preparation options lets us fix, in this case, a quick mix to do the mixing, as well as an MVAP to evaporate the samples and derivatize. Shown here is actually a dual head system as a workstation, but this can also be placed on top of a GC triple quad if you wanted to do the analysis afterwards. Next is an example of a workstation. Sorry about that. I just got to notice that my battery's low. For performing dual derivatizations, a lot of the proteomics people require 2 different temperatures to be used during derivatizations, and the MPS can be outfitted with 2 different temperature zones if you need. The polymer chemists, if you need, we've worked with, these are stir plates that allow 100 milliliter of vials to be stirred. In this case, we have a pump that is connected to a valve to allow the transfer of large volumes to dissolve the polymer first, and then we move that over to a heated stir plate, which is in the center. Once that's dissolved, then the valve is switched, and we add the crash solvent to it, which then on the right of the picture shows another syringe module that will come over and pick up the known amount and put it in a vial, and then the analytes can be analyzed offline by LC. Let's see. We also just had a dual needle concept in order to vent, because whenever you're adding large amounts of solvent in a sealed vial, you'll need to vent off some of that gas that may be built up. And of course, we can automate the preparation of standards. So it's shown here is a nice dual head rail that has in the far end there, going from the far end in the picture, it's a robotic pro, which has that tool exchange. So we can have like a 10 microliter syringe, a 100 microliter syringe, and a 1 mil syringe to be able to transfer whatever volumes we may need whenever we're preparing standards. We have the Sartorius Balance, of course, to get weight verification. We have you can't see it, it's the red module behind the wash stations there. That's the quick mix for mixing the samples. But then in the foreground here, the left side, we have that 5-position diluter to add the various diluents that we may need depending on what standards we're preparing. That's all software designated. Drop down menu, choose acetonitrile on Monday, choose methanol on Tuesday, and then we even have a Peltier cooled stack here. So if your standards are thermally needed to be regulated at a certain temperature, or if you want to prepare the standards, overnight, you're preparing your standards and you want to stick them into a refrigerated unit so that they can be stored until you come in during the day, and then you take them off and then you analyze them whenever you get in during the morning. So basically we tell our users, think about your manual steps, what you're doing, and then give us a call and we can work with you to pull those automated sample preparation modules that we have and basically configure a system to perform your exact method in order to free up that time and get through all those samples that we're all going to have whenever we're getting back to work. There's a wide variety of different application notes available on our website down here at the bottom, gerstlus.com. It's easy to search. Feel free to jump online and look around. But for the most part, we're all in this together. We all got a lot of data to do. We're all looking for the best ways to get through the data that we need to get. And that's where that MPS comes in, that automated sample preparation. Let it do the sample prep at night and even inject it. And we can better serve our time, analyzing the data and making those decisions that we need to make. But I'd like to thank you for your attention and for, joining tonight's meeting. Gerstl's a family-owned German-based company with a global reach. It's been in existence over 50 years. And it's been a premier provider of automated solutions for sample prep and introduction. We like to say, no other company has a bigger toolbox of sample introduction and preparation techniques. So thank you very much again for asking me to talk, and I can answer any questions that you may have.
Wonderful. Thank you, Fred. What an excellent presentation. There's a lot of stuff to consider. So if you would like to ask a question of Fred, you can go to the chat box or to I believe the chat box, type it in and we'll answer your question. We have some time here for several questions. While we're waiting for the first question, Fred, I do have a question for you.
Yes, sir.
So if you've got a team that is looking at automating a multi-step manual sample preparation, and for this discussion, you could assume that this sample is an SPE type procedure. You've got the team; they're all excited and they're all bright-eyed and bushy-tailed and optimistic and everything. And oh my God, we're going to automate this thing to the nth degree. Mm-hmm. Before they get started, what would be a couple of pieces of advice from someone who's been there before?
Well, take a look at your method first of all, right? So it depends on the method, right? If you want an automated an SPE method that uses 1 liter of water sample, and you need to pass that through a cartridge and then elute it. Our modules can do that, but it's going to take a long time to do that. You may need to. What are your detection limits? Can I get away with using less sample? You've got to think of, I've got a manual procedure, but how set in stone is it? So am I able to scale down as long as I meet my limits of detection? You got to be, if you have a step where you have to add concentrated nitric acid, that may not be good for an automated platform, or that may be a step that you need to do manually. So there's things that you've got to think, yes, I can do this manually, but can a robot do this as well? Right? So, turning it on its side in order to aspirate that little last bit is tough, for an XYZ robot.
Excellent. Thank you, Fred. One of the questions that we have in from the Q&A is, this one's a little more specific.
Oh.
Can I change an inlet liner on a GCMS between sample or extraction types with the Gerstle?
Yes. Yeah, we have an option called the Alex, is automated liner exchange. And what that does is in the sequence table, you can tell it where, if you want to do it every 5, you just put that in. And then after that 5th sample, it will go and put in a new liner for you.
I think that is a question for the poster. Let me come down. Robin, if you see one of the questions, step in, please.
There was that one that I just sent over to you that you just asked. So I'm not seeing anything else yet.
So do we have any other questions for Fred here today? So I do have one last one while we're waiting for another question here. What are a couple of pitfalls that you see teams go through or major obstacles when they embark on converting over from manual to automated extraction procedure?
From the I would say industry side, going, well, not industry, but from the supplier side, right, of automation. Don't be afraid to ask questions. Don't be afraid to call the company that you're working for, regardless if it's Agilent or Gerstle or Thermo or whoever, because they're here to help. The hardest struggles are usually can be answered quickly on the phone by just, calling or emailing. So, I mean, never be afraid to ask a question. It can save you a lot of headaches or struggles or stress. We don't need more stress right now, right? We just need systems to work. So don't be afraid to reach out. That would be a big pitfall that I can see new users who may not be familiar with the software or the hardware and may be hesitant to, I don't want to touch it, because it's not working or it's working right now. And please reach out to the companies. They'll help you.
Got you. So I don't think I see any other questions. Robin, do you see any more?
Yeah, I just sent you Merlin has a question. Did you see it in chat?
Let me go back to chat. No, can you read it, Robin?
Yes. The question from Merlin, what is the least precise individual step for this system, and what would be a typical RSD value for that step? In other words, what is the weakest link in this chain of procedures?
Good question.
That's a general question, which is good, I guess. I would say, you got to be careful of your sample, right? So think of, we have options that can help with viscous samples, okay? Because just because it's technically a liquid doesn't mean that it's easily aspirated and dispensed using a syringe. Ketchup is technically a liquid, but it's very tough to accurately transport that sample. Now we have things like heated syringe modules that can help warm the sample in order to help it get transferred more easily. But a lot of the concentrated acids, the more viscous samples, you may not be able to get the best reproducibility after that. So on a typical syringe-based system, you should be experiencing 2 to 3%. It would be generous on that. I've done some work on just looking at the diluter and the syringes with that balance option, and I'm getting less than 1% RSDs during my multiple transfers. But that would be a typical, and that's all based on the syringe manufacturers. They're all state that you got 2% or less. Or
got another question here, Fred, about the 96 plate well. I know you're talking about with the SPE cartridge, like right on the instrument, but what about doing the entire 96 wells at one pop?
Our instrument can't do that. We're a syringe based, so it's one cartridge at a time. Now, that being said, we can use 96 well plates like the ITSP cartridges. We can dispense into a 96 well plate. So
Gotcha.
we pick up 96 of those cartridges and dispense it into well plate. But those, Waters or whoever, Phenomenix has those SPE plates that are sort of on top of a filter, and we can't handle those. Those can't be handled. But once you do that and you have your eluents in that 96 well plate, you can certainly put them on the MPS to further process or inject them or anything like that.
So again, these are some questions that you need to answer before you start down the road of automation.
Right.
All righty. Any other questions? One last chance here. All right.
Yeah, there are some questions.
There are?
Did you see the question from Anne? And open your chat. Do you see the question from Anne? I can just ask it. So for
Yeah, I don't
Anne,
see it.
there's a couple here. Fred, in your experience, what is the average setup time from the day that MPS arrives until you can run samples for an SPE extraction process?
Well, typically whenever, I'm sorry. I think I just stopped sharing my screen. Typically, whenever you're doing a configuration that is set up for a specific method, we'll usually send a test prep sequence. So the service engineer sets up the system and he needs to test it out to make sure it's performing. And that'll usually be already, one of us back at the lab will have written that prep sequence. So you should be able to start at least with a basic SPE method that you've come to us with to automate. After he's done, you should be able to start, running your samples. Now, if you just have a basic one and then you want to develop another method, you may need to learn some of the programming, which it's not that hard to learn. But the nice thing about the having an autosampler is you can do that method development. You know how like you're eluting with 5%, then 10%, then 15%. You can set that up on the autosampler and let that do it, and then just inject the samples, and then come in and say, oh, look, it looked like 30% elution or 30% wash took care of the majority of my matrix issues. So.
And here we have a question from Todd. Any experience with orange juice automated preparation? Talking just a simple dilution prior to SPE or aeroSPE?
Yes, it can be done. I've worked with orange juice, but not with SPE directly, but I have. And usually what we're doing was, adding internal standards to the orange juice and then diluting it and actually filtering it before an LC. But for SPE, it would be the same thing. I mean, you would dilute the orange juice with whatever diluent you have, and then pick up the SPE tool, right? And then do the, move it to the agitator, do the SPE if you needed to. So.
Excellent. Robin, do you see any other questions?
Something just went into Q&A. Let me see if I can pick it up. From Natalie, is there a higher level of maintenance needed with automation than with a manually operated instrument?
They're both sort of, I mean, they would be sort of both the same, I think, if I understand the question. I mean, if you're injecting a sample into a GC by yourself, you might have to worry about blisters on your fingers or something like that. But if you're meaning like as you add modules, you need to increase, the amount of service. They're pretty robust, so there's not, I mean, maybe keeping them clean. If there's a motor in it, making sure that the bands are working.
See if we got any more questions.
There's one from Andre. Just a second. From Andre, do you recommend lowering your sample load and moving to automation at the same time, or do you recommend doing them separate?
I'm not sure what do you think Andre means by sample load? Does it mean maybe scaling down the whole thing and moving to automation?
Andre can, he's a panelist. Yep, there he's going.
Yeah, so
you can unmute.
Scaling down from a large volume usage to smaller load sizes of cartridges, therefore smaller amounts of sample.
Right. It would depend on how small that you need to go in order to automate. I mean, you could test it out to make sure you're getting your detection limits using that smaller volumes of everything. But you could do the same thing using an automated platform and just continually scale down and have the auto sampler analyze everything.
Thank you.
Any other questions? Robin, do you see any?
Todd had a comment, so you'll like this, Fred and Sean. Just a comment. So far, our Robotic Pro has been awesome and robust. Love the ability to change the tools. So just a comment.
Very good. You got a fan.
Thank you. We like it too.
All right, one last question. Anyone? You see one, Robin? I think you see him like a little bit before I do.
I'm not. Nope, still not seeing anything. We might have answered. He might have answered them all.
All right. All right. So, Fred, thank you so much for coming here and presenting this presentation for us tonight. This is a very interesting topic, and anyone in the lab business understands the importance of getting around this and moving on. So thank you for being our first presenter at our first virtual presentation platform here. And so thank you very, very much.
Thank you. Thank you all. Thanks.
And with that, I bid everybody a good night, and thank you for attending the CCDG technical meeting this quarter.
Thank you.
Thank you.